Hey y'all, today we're going to be continuing our talk of U sub, so day 2 of our U sub notes. And what we're going to explore today is some extra situations where we have to do a little bit more for our U substitution. Because they're not all going to be nice and pretty like last classes, if you would consider last classes nice and pretty. So the first situation we're going to look at, and you probably saw this already if you're kind of glancing through the notes, was U substitution where the X term, that term in the front that we're trying to get to cancel out, doesn't actually cancel. So let's look at number 9. Number 9, we have x times x minus 3 cubed. So we can still see pretty clearly here that x minus 3 is our trapped term. So our u should still be x minus 3. Okay, but what you probably already picked up on, as it's what it's called, is that the derivative of x minus 3 is not going to be x. We're not going to be able to cancel out that x term. Okay, so let's go through the motions anyways without doing this extra step, just pretending like we didn't know we need to do this yet. So then from here, I would take my derivative. So du is equal to, derivative of x minus 3 is just dx. Okay, so that's already done. So this becomes the integral of x times u cubed times dx is just equal to du, so I just plug du straight in. Okay, so we can see pretty clearly we're not going to get that x term to cancel out. So what we have to do is we actually have to find out what x equals. And this happens anytime you get that x term to not cancel out. You want to check and see, okay, can I solve my u equation so that it equals whatever I haven't gotten to cancel out, whatever x term, maybe it's x squared, maybe it's x cubed, maybe it's sine of x or cosine of x. But can I solve that equation for that term to then be able to plug it in? So here, u equals x minus 3. I can add 3 to both sides. So I get u plus 3 is equal to x. So then I can additionally replace that x with u plus 3. So we get u plus 3 times u cubed du. So now this looks like our more traditional, it's a product rule. I can't integrate a product. So first thing I want to do is I want to distribute that u cubed. So this becomes the integral of u times u cubed is u to the 4th plus 3u cubed du. Okay, so now instead of just having a single u term, now we kind of get this polynomial of u. So I can still go in and integrate. These are all going to be power rules. So this becomes u to the 5th over 5 plus 3u to the 4th over 4 plus c. And from there, I'm still going to plug in for u, but now I have to plug in for all of my u's. So since I have multiple u's, I'm plugging in that x minus 3 in multiple spots. So this becomes x minus 3 to the 5th over 5 plus 3x minus 3 to the 4th over 4 plus c. So the nice thing about these ones where x doesn't cancel is, once again, kind of like our other u subs, they all kind of usually fall out in the same way. They look the same way in their final answer. You get those multiple power fractions kind of set up in your final answer. So once again, they look similar as you do more and more, so you get to kind of be able to recognize them. So let's look at another example. Let's look at 10. So we have x times 2x plus 5 to the 4th. So once again, we can see pretty clearly derivative of 2x plus 5 is not going to leave us over with an x, so we're going to have to replace. But let's go ahead and take out our u. So u is equal to 2x plus 5, which means du is equal to 2 dx, which means du divided by 2 is equal to dx. I also need to, I already know that x isn't going to cancel out because I can see I'm plugging in du over 2, so I'm not going to get that x to cancel out. So u minus 5 is equal to 2x, which means u minus 5 divided by 2 is equal to x. So I have two things I can replace, x with u minus 5 over 2, dx with du over 2, and then of course my 2x plus 5 with my u. So this becomes the integral of x becomes u minus 5 over 2 2x plus 5 to the fourth becomes just u to the fourth, and dx becomes du over 2. Okay, from here I can simplify a bit. I can take those 1/2 out, so this becomes 1/4 times the integral, and then distribute that u to the fourth inside, and I get u to the fifth minus 5u to the fourth du. And then we can integrate from here. So just like last time, but I do have that 1/4 in front, so 1/4 u to the 6 over 6 minus 5u to the 5th over 5 plus c. And then from here, we can do some simplifying and plugging back in. So 1/4 times 1/6, that's 1/24. So this becomes 2x plus 5 to the 6 over 24 minus 5 and 5 cancel out. So it's just going to be the fourth. So 2x plus 5 to the 5th over 4 plus c. And you can really keep it like this, y'all. I mean, you don't have to simplify further. Obviously, if you see on an exam, like as a multiple choice question, you see it combined and condensed into one single fraction, you might condense it into a single fraction. But typically, this kind of broken up fractions is usually how you'll see it even on an exam. But if you ever look at your answer choice and you're like, I know I did everything right, but my answer choice doesn't quite look right, then just see if you can simplify, condense into a single fraction. Maybe take a GCF out. Like both of our terms have 2x plus 5 in them, so you could take out a 2x plus 5 to the 5th power and simplify from there. But other than that, that should kind of square it all away. All right. We got one more. I forgot. This one's weird. So I'm going to let y'all try this one on your own real quick. So pause me. Try this one on your own. You're going to get some fractions. So yay, fractions. But pause me, then unpause me, and you can check your work. All right. So just to check, you should have gotten u equals 2x minus 1 as your u. Our x would be u plus 1 over 2. Our dx would be du over 2. So when we plug in, we get u plus 1 over 2, u to the 1/2, and du over 2. We can pull that 1/4 out and distribute the u to the 1/2. So we get 1/4 u to the 3/2 plus u to the 1/2. And then from there, we can integrate. So u to the 3/2 becomes u to the 5/2 over 5/2 plus u to the 1/2 becomes u to the 3/2 over 3/2. And then just slowly simplifying, plugging back in, we finally get 2x minus 1 to the 5/2 over 10 plus 2x minus 1 to the 3/2 over 6 plus c. So as we start to get into these weird special conditions, you can start to notice these functions get really gross. I mean, is this function necessarily going to represent something in real life? Maybe, maybe not. But remember, right now in the nitty-gritty of calculus, it's really just testing, do you have all these skills? Not necessarily like, hey, this function models, the boiling temperature of hydrochloric acid. Like, no. But real world application, not applying here, not applicable. The second situation that we're going to talk about is u substitution for definite integrals, which this is our fundamental theorem. Remember, anytime we add in our a to b, it's fundamental theorem of calculus, or FTC. But really, it's just a fundamental theorem it's the definite integral. We're actually integrating with numbers. Okay, so this one, we call it the change of base u sub. And the reason why is because when we actually do the process of u substitution, we're substituting one function for another. So we are actually fundamentally changing the function we're integrating. So when we fundamentally change the function we're integrating, we can't use the same original limits that we had before we did the substitution. So we change the base, we change our limiting space using the u that we got. So let's actually see it in action. So we have the integral from 0 to 1 of x times x squared plus 1 cubed. So u is our trap function, which is x squared plus 1. So u is equal to x squared plus 1, which means du is equal to 2x dx, which means du divided by 2x is equal to dx. Okay, the second thing we need to do is we're going to change our base. We change the base by taking our A and plugging it into our U equation and taking our B and plugging it into our U equation. So let's look at this real quick. So plugging in 0, so U is equal to, I plug 0 in for X because it's an X interval. So U is equal to 0 squared plus 1, which is just equal to 1. And then my second one is 1, so U is equal to, not green. U is equal to 1 squared plus 1, which equals 2. So my new interval is going to be 1 to 2. So let's set up our integral real quick. So this becomes the integral from 1 to 2 instead of 0 to 1 of x times u to the third times du over 2x. So like normal, I get my x and my x to cancel out. I can bring that 1/2 out, and we get 1/2 times the integral from 1 to 2 of u cubed du. Okay, so our regular, u sub stuff is like a normal u sub. It's not that one where x doesn't get to cancel out. So the only special thing we had to do here is we had to do that change of base. And I want to show you real quick. I know you're probably like, well, yeah, I can see that function is different, but I want to show you how these functions are actually different. So our original function, and see real quick as I wait for Desmos to show up. There we go. So our original function was x times parentheses x squared plus 1 cubed. So x times parentheses x squared plus 1 cubed. Okay, so that kind of actually fairly normal looking cubic function. And we were integrating it from about 0 to 1. So kind of this little curvy triangle right there. Our new function is actually just u cubed. Oop, not u cubed. You have to use x cubed still when you're graphing in Desmos. Okay, so our new function is x cubed. So see how that's a completely different function? So if I integrated u cubed from 0 to 1, I would just get that little tiny area. And that wouldn't work. Okay, so, but if I shift it over, I'm now integrating the area from 1 to 2, which that total area looks a little closer to the total area under my original function, which was from 0 to 1. So that's why we actually have to shift over. We have to change that base, because if we use the original base or the original limits on the new function, then we're not going to get the right area. So because we've changed the function, we also have to change the base. So I just want to kind of make that clear. I wish I could highlight this area. That would be really cool and useful, and then show you. But unfortunately, barriers to technology. Okay, so let's keep on keeping on. So we have the integral from 1 to 2 times 1/2 of u cubed du. So this is a super easy integral. Integral of u cubed is just u to the 4th over 4. So 1/2 times u to the 4th over 4. And I'm evaluating it from 1 to 2. So now my f of b minus f of a. Oh, but you might be thinking, but Mr. Arbone, you need to plug back in for u. I don't need to plug back in for u because I've now integrated my u function with my new interval. So I don't have to plug back in x squared plus 1. So because I don't actually have to plug back in x squared plus 1, it actually kind of makes it a simpler integral, because I don't have to plug that back in and then do the x squared plus 1 times 2, all the mess. I just have to do to the 4th over 4. So this becomes 1/2 parentheses 2 to the 4th over 4 minus 1 to the 4th over 4. Which 2 to the 4th is 16. So this is 1/2 16/4 minus, that half looks more z-ish than 2-ish. So 1/2, 16/4 minus 1/4, which is just 1/2 times 15/4, which is equal to 15/8. And that's our answer. So even though you have to do some extra work up at the front where you do that change of base step, it makes it a little easier in the fundamental steps towards the end because you don't have to plug in as much nasty grossness to simplify out your answer. Okay, so that is U substitution with a change of base. Technically, you could have U substitution with a change of base and also where x does not cancel. You could get both of those in the same problem, but unlikely because that's a pretty long, arduous, difficult U substitution. But I will let y'all, or we'll do one more together. I won't make y'all do another one by yourself. Okay, so 13. We are finding the integral from 1 to 5 of 1 over the square root of 2x minus 1. So this one doesn't necessarily look at first glance like a U substitution because you're like, well, there's no other x term to start on. There's just the 2x minus 1. Well, the derivative of 2x minus 1 would just be 2, so I don't need any x to cancel out because I don't have any other x in there. But I still have a piece that's trapped. 2x minus 1 is trapped inside my square root, so I still have to do U substitution. So U is equal to 2x minus 1, which means du is equal to 2 dx, which means du divided by 2 is equal to dx. Okay, good so far? So then from here, I need to do my change of base because it's the u sub of a definite integral of that fundamental theorem. So u is equal to 2 times 1 minus 1. So 2 times 1 is 1, or 2 times 1 is 2, minus 1 is 1. And just so we still know, we'll make that red. And then my other change base is my 5. So u is equal to 2 times 5 minus 1. So 2 times 5 is 10, minus 1 is equal to 9. So my new b would be 9. So then I'm plugging everything in. So my new integral is the integral from 1 to 9 of 1 over, instead of the square root of 2x minus 1, I'm going to do u to the 1/2. And then instead of dx, du over 2. So then before I integrate, I can do a little simplifying, bring that 1/2 out, integral from 1 to 9, and this becomes u to the negative 1/2 du. All right. So good so far. Let's keep working. So the integral of u to the negative 1/2, add 1/2, divide by the new power. So this becomes 1/2 u to the 1/2, divide by 1/2, and we're evaluating it from 1 to 9. Now, fun fact, you haven't seen me do this before, but you can actually simplify your constant that's being multiplied outside before evaluating your integral. So the reason why is because it's pretty clear to see that 1/2 and dividing by 1/2 are actually going to simplify. That's awesome. So then this is just the integral of u to the 1/2 from 1 to 9. That's super easy. This is equal to the square root of 9 minus the square root of 1, which is equal to 3 minus 1, which equals 2. So the pre-work was hard, but man, if that wasn't the easiest fundamental theorem of calculus you've ever evaluated, square root of 9 minus square root of 1, no gross fractions to mess up. So sometimes calculus is nice and pretty. Okay. So that is really the two new skills we're talking about today is u substitution where x does not cancel, and then u substitution for definite integrals or a change of base. This last page, if you want to go ahead and try these questions, you can, but I'm actually going to talk about these as our in-class notes. Okay, so you don't need to worry about 14, 15, 16 right now, but if you want to go and work on them, feel free to, but I will talk about them in class. All right, y'all. That is U substitution in a nutshell. Next couple of days, we'll do E and natural log and finish out our integrals. But other than that, thank you for watching.